industrial automation. Let's start with a short introduction. Let's start with myself. I will be your host today. My name is Thilo Gemeinhardt. I'm based in Munich and responsible for sales in southern Germany and Austria. And now, Andre, can you please introduce yourself?
Yeah, thank you very much, Thilo. My name is Andre Kipp. I'm a project manager at InfraTec for the thermography systems in some parts of West Germany and Benelux. And I'm happy to tell you something today about thermography and in InfraTec's camera portfolio, and also join later the Q&A session to answer your questions you will have during the webinar.
Okay, so let's have a look at the agenda for today. So we will start with introduction, then we will follow up with the thermography and information about thermography and about our camera portfolio, move on with the software and software integration, and then we will show the automation turnkey solutions that InfraTec is offering. And then, we will have the question and answers session. Okay, so now let's start with the introduction.
Hello, everybody. So let's start with an introduction. With a quote from Lord Kelvin that said, if you cannot measure it, you cannot improve it. So this is the topic of automation, to measure things, to improve things and processes. So let's start with the introduction into infrared thermography. What is infrared thermography? Thermography is a contactless imaging and measuring of infrared radiation. So what is infrared radiation? It's the electromagnetic radiation beyond the visible. So it's called thermal infrared. As you can see below, there are three bands in the thermal infrared. It's mid-wave infrared and long-wave infrared that are mainly used for thermography. And there's also the short-wave infrared that is usable for high temperatures. Let's move on. We are using an imaging camera. That means there is a two-dimensional array of sensor pixels that collect infrared radiation. And in terms of cameras, there are two different types. There are uncooled thermal detectors, also called micropolarimeters. They are mainly used especially in automation. On the other side, we have the cooled quantum detectors that are used more in R&D and special applications. So there we can see an overview how that looks like. Typical setup, a lens. We have a detector, also called focal plane array. And that can measure the image or the infrared radiation. Okay, let's move on. In terms of, so we can collect the infrared radiation in terms of measurement. If we want to have temperature values, we need to do a conversion of the detected infrared radiation into absolute temperature values. This requires a calibration that is done in the calibration lab. And it also requires an emissivity correction, depending on the sample that needs to be measured. So let's have a summary. Thermography is an imaging method of precise and contactless temperature measurement. And the result is a thermal image, as we can see over here. In terms of thermal cameras, there are three important features to differentiate cameras. It's first, the thermal resolution. So this is the smallest temperature difference that can be differentiated. This is commonly expressed by noise equivalent temperature difference, NETD. Move on to the spatial resolution. This is the number of pixels and pixel size that defines the spatial resolution. And then we have, depending on the lens, we have an resulting field of view that we can resolve. Last but not least, we have the time resolution. This is the speed or frame rate that is defined in frames per second or hertz. And these three parameters are main camera cost drivers. So higher resolution, higher speed also increases the camera price. Now let's have a look into automation, the topic of the webinar. First of all, what is automation? Automation describes a wide range of technologies that reduce human intervention in processes, mainly by predetermining decision criteria and related actions in machines. That means there are rules defined, and based on inputs, machines make decisions. So there isn't no human needed anymore, so machines can make decisions on their own. And this automation market is a huge market, is a growing market, and the key driver is the growing need for inspection and automation. First of all, to reduce cost and also to improve quality. And in order to do so, in order to automate things, sensors are required. Machines need inputs to make decisions, and machine vision with camera-based systems plays a major role in that automation. On the right side, we can see some charts. Don't want to go into the details, but we can see that the automation market and the machine vision market is expected to grow even more in the future. Now there's the question, how does thermography fit into that picture? Let's have a look on the next slide. Here I would like to show a typical machine vision inspection system where we have, like on a conveyor belt, it's an inspection system to check parts on the conveyor belt. So it's the conveyor belt, it's the parts on the conveyor belt. We have camera and optics to acquire the image. In the machine vision visible image world, we need illumination. Then the data is transferred to an image processing software that makes decisions to say what's to pass fail, so what's a good part, what's a bad part. And then there is some process control interface to reject the bad parts. On the other side, we can now look at the thermography inspection system that would look very similar. There's a camera. In that case, it's a thermal camera. No illumination is needed because we measure directly the temperature. And as a result, we have a thermal image instead of a visual image. But we can make the same decisions, good parts, bad parts, and so on. So as a conclusion, thermography and the automation field is closely related to machine vision and very similar. I mentioned before machine vision and then the machine vision cameras. They are based on visual image. It's typically a visible range, but it can be also UV. It can be also near-infrared, shortwave infrared. In that field, for the cameras, there are highly standardized interfaces and software. And there's for the standard software for imaging processing. So it's very, very easy to build a system based on standard components. There's really a complete ecosystem of camera software that can really plug and play work together. So I will explain later a bit more about the Gigi Vision and the GenICam, but that's the main driver to create that ecosystem. On the other side, on the right side, we have the thermography, the thermal cameras, where the decisions and the results are based on thermal images and temperatures. The range is the thermal infrared, the shortwave up to the long-wave infrared. In terms of standards, there's not really a standardization for this kind of data. So there's typically proprietary solutions of camera manufacturers that offer own SDKs for the integration. However, there is a trend in the thermography world to adopt a machine vision interface to allow easier software integration. So let's move on in terms of the demands for automation versus the research market. So we are covering both markets. Let's start on the left side with the research market. In the research market, the basic driver is to understand the processes. The needs are, it requires the highest precision in terms of thermal, temporal, spatial. It requires flexibility because it's really an approach to understand processes. In terms of application specific is typically a camera is chosen for one application, but of course there needs to be some long-term flexibility to adapt as needed. There's typically one-by-one systems, there's not so much repeatability, and typically customers using lab software or SDK from a camera manufacturer. On the other side, we have on the right side, we have the automation market. And as we can see, there's some adoption process that typically, first in the research market, processes are optimized, and then in the automation market, it's more about controlling and monitoring parameters. The requirements are more on the long lifetime, low cost, and is basically just fitting the needs of the application. It's rather non-cooled cameras, and only a few applications are asking for cooled cameras. In that field, it's enough to serve one specific application. But typically, this is then it can be duplicated. That is, if it works on one line, it's adapted to multiple lines for inspection and so on. So this is more a market where it's possible to sell several systems. And integration is the requirement is to use standard interfaces to allow an easy integration. So to summarize the automation requirements, it's a cost-driven market that requires just good enough solutions that are easy to integrate. So now let's have a look at the camera that fits very well for automation applications. This is our Taurus IR Mini. It fits well with the pricing, so that such kind of cameras make thermography affordable, especially this micropolymmeter cameras as the Taurus IR Mini. So the pricing is below €7,000 for a VGA resolution, and that allows to use such cameras instead of other point measurement devices, where we can only measure some points. With the camera, it's possible to measure a complete area in one shot. So let's move on in terms of integration. And this camera has a very compact size. It has standard software, GigaVision GenICam. So this allows easy integration in terms of hardware and software. So let's move on to the specs. So the specs fit many applications. It has a very good thermal resolution and also a broad temperature range. In terms of spatial resolution, it has VGA resolution and has a flexible field of view with 5 different lenses. Last but not least, it's also rather fast for a micropolymmeter camera with up to 50 Hertz. So let's summarize. Micropolymmeter cameras as Taurus IR are suitable for a wide range of applications. The only limitations are fast processes and movement due to rolling shutter of such micropolymmeter cameras. So let me now introduce 2 different ways for thermography. So the mainly used application is passive thermography, where we measure directly the temperature of an object. So this is kind of the standard application, and we measure the existing thermal radiation of an object. On the other hand, we have active thermography. This is a bit different because we make an active excitation, and we measure the temperature response to find defects. Yeah, so it's also this belongs to the non-destructive testing. So we generate some heat in the test object, and then we measure the temperature response to find defects. As we can see below, there's different ways to make this excitation. It can be internal, it can be external. And here we can see if there's some defect, we can see temperature differences with the camera. And this allows to make testing. So let's now move on. In terms of application fields, we have three different application fields. So the first is condition monitoring, where we monitor processes and conditions in terms of to avoid fire, in terms of safety. So one example is waste bunker monitoring to prevent fires. Another one is steel mill ladle monitoring to avoid that it gets too hot, that it melts. Let's move on to the second part, process control and quality assurance. So here we monitor processes, temperatures in processes, like press hardening, where we inspect the parts after press hardening. So we measure the temperature. Another one is slag detections, where we use the cameras to detect slag in the steel manufacturing process. So here it's about monitoring processes to assure quality. Last but not least, we have the non-destructive testing, the active thermography that I have explained before. Some examples here are weld inspection. So we use excitation and then to check the quality of welds. Or here's another example to check like surface coatings. There's also excitation and then to check the coatings. So let's move on. So there are some examples. There's another slide with even more examples. So I don't want to go in all the details, but there's many applications really to use this thermography in automation applications. So let's proceed with the introduction about InfraTec. InfraTec is a company, is a privately owned company that was founded and is based in Dresden. It was founded in 1991. It has a staff around 250 employees, and the sales with approximately 45 million in 2024. The company is a specialist in infrared technology, and it has two business units, the sensor division and the infrared measurement division. On the left side, we can see that our worldwide presence. So we have offices in some markets, and we also work together with sales partners. And at the bottom, we can see how the headquarter looks like. So InfraTec is based in these two buildings. One is newly constructed. So let's give a short introduction about the sensor division. The sensor division has an own production clean room and offers pyrometers. So pyrometer, digital infrared detectors, and they are used for example for gas and flame analysis, heat and fire detection, as well as other optical measurements. Let's move on to the Infrared Measurement Division, that's the division that I belong to, that takes care of the cameras. So we are offering thermographic systems for research and development, for non-destructive testing, for process and quality control. As well, we also are offering turnkey solutions for process monitoring, fire detection, and surveillance. Last but not least, we are offering training courses, service, software, and of course, support. Yeah, so we are a one-stop solution for a wide range of applications. As I mentioned, the camera, so we cover a broad range from shortwave to long-wave infrared. We cover cameras from small to large, small resolution up to high resolution. So we will explain you more about that in the later section. We are offering extensive software solutions for the cameras. And as I mentioned, we're also offering turnkey solutions. We will explain more about that later. And as well, solutions for non-destructive testing. And as we can see here, we have sold more than 8,000 thermography solutions for customers worldwide. And here we can see some reference customers. So much for the introduction. And now let's move on to the next section. Thanks.
Okay, so yeah, welcome back. Let me share the agenda once more. So now we have finished the introduction, and now we move on to the next topic where my colleague has prepared an overview about thermography and camera portfolio.
Welcome to today's presentation of infrared thermography and InfraTec's camera portfolio. Throughout the session, I will provide a comprehensive overview of infrared thermography, explaining its principles, and we will also take a closer look at InfraTec's advanced thermographic camera technologies. Infrared thermography has become a real game changer, especially in industrial quality control and process monitoring. It makes visible what the human eye cannot detect: temperature distribution, without contact, in real time, and with high precision. The great advantage: we can observe and analyze processes without interfering with them, and from a safe distance. It helps us to understand better, which means we can control better. What makes temperature measurement possible? Temperature can be transferred through three physical mechanisms: conduction, for example in solid materials, where classic sensors like thermocouples are used; convection, through moving gases or liquids, such as air; and, most importantly for us, radiation. The radiation does not need a direct contact. We can simply capture it with the camera. This is where infrared thermography comes into play. It makes visible without a medium for transmission, even in a vehicle. Thermography often sounds technical at first, but in practice, it is surprisingly simple. Instead of installing complex sensors, thermography often only requires one look through the camera. The heat distribution on a surface becomes immediately visible, without contact, quickly and reliable. Of course, physical properties like emission, reflection, and also the transmission play a role. But for many standards application, it is enough to know or estimate the emission level. And it's the advantage of thermography. It enables fast temperature analysis without interrupting the process. Infrared radiation is a part of the electromagnetic spectrum, the range of wavelengths we can technically use. Our thermography cameras primarily operate in the mid-wave and in the long-wave ranges. In these spectral regions, the atmosphere is mostly transparent, despite water vapor, dust, or other interferences. This ensures a clean, precise measurement, even over long distances. Shortwave infrared ranges are mainly used in laboratories for laser applications, for example, or in special high temperature scenarios. The atmosphere plays for infrared radiation a key role. The air, especially when humid or dusty, can weaken or even block radiation completely. Today, we know that the mid-wave and the long-wave infrared ranges are the best for the most applications since they are relative atmosphere friendly. For very high temperature processes or laboratory conditions, shortwave infrared cameras can also be used. In the theory, we often work with the black body, an ideal emitter that radiates 100% of its energy. In practice, real materials behave differently. They do not only emit heat, the emission, but can also transmit or reflect radiation. For most applications, knowing the emission level is sufficient. Reflection and transmissions are often less significant or can be corrected if needed. Even through this physics behind thermography is complex, but with just a few settings, the camera provides usable results quickly. A great example is glass. In the visible range, glass is transparent. We all know this, but in the infrared range, its behavior is much more complex. In the mid-wave range, glass allows some radiation to pass through. In the long-wave range, we have no transmission, just emission and reflection. This shows that we need to analyze the material we are observing and choose the best camera for the job. Now for the exciting part, which camera systems is the best suited for your application? We differentiate between three categories. Compact cameras, small, robust devices for simple applications. System cameras, ideal for laboratory and industrial use. High-end cameras for application with exceptionally high requirements for resolution or speed. We offer solutions for everything, from the entry-level models to the special systems. Let's look at the technology behind it, the detectors. We distinguish between two main groups: cooled quantum detectors, extremely sensitive, often made with materials like MCT or InSpi, or uncooled microbolometers, robust and maintenance-free. Cooled systems provide fantastic performance like thermal sensitivity and high frame rates, bigger FBR sizes or faster response time. However, they are also bigger in the invest, and uncooled cameras are more compact and easier to integrate. When discussing detectors, we should also consider images capture methods. There are two fundamental techniques. On the left side, snapshot detector, where all pixels are captured simultaneously, typical for cooled quantum detectors. On the right side, rolling shutter, where pixels captured line by line, typical for uncooled microbolometers. Snapshot images have a clear advantage for fast-moving processes. Rolling shutter, on the other hand, is technically simpler, making camera smaller and more affordable. Let's have a look on the characteristic of an infrared camera. Three aspects are important. First of all, thermal resolution. How finely temperature differences can be measured. The lower the NETD, the better. The spatial resolution, the number of pixels. Also the detector size and the lens matters. And the time resolution, temporal resolution, frame rate and reaction time. The thermal resolution we see here clearly. With a camera that has a high thermal resolution, for example 20 millikelvin, we can detect tiny differences in temperature distribution. With lower resolution, the image appears rough or noisy, like here 50 millikelvin thermal sensitivity or 80 millikelvin thermal sensitivity. For sensitivity application, the value is critical. The images shown come from an uncooled microbolometer camera, demonstrating how much is technically possible today, even without cooling. Let's have a look at the spatial radiation. The number of pixels makes a difference too. On the left side is an image we made with a low-resolution camera. On the right side, an image that we made with a high-resolution camera. The result, only with sufficient pixels, we can accurately measure and detect objects. You can see here, on the left side, we measure 61 degrees. On the right side, we are measuring 80 degrees. Let's have a look at the time resolution. Time or temporal resolution is important for fast-moving or rotating objects because of the short integration time of such infrared cameras. Uncooled cameras like microbolometers have a certain delay, which can cause smearing effects in fast scenes. Before we dive deeper into our camera technology, here's a quick recap of what we covered so far. We have explored the basics of thermography, from physical principles to camera classes and technology parameters. Next, we will look at our products for the industrial automation. Now let's talk about a true quality feature, the calibration. All of our cameras are radiometrically calibrated. This means they provide accurate measurements with a calibration certificate. They even come with multiple calibration curves, ensuring stable results, even if ambient temperatures fluctuate. Especially in automated systems, where multiple cameras work together, is precision essential. Our camera portfolio covers every application. High-end cameras, offering maximum performance. System cameras, ideal for industrial environments or laboratories. Zoom cameras for long distances. Compact devices, here the Taris Mini stands for. An extremely small yet powerful camera, perfect for tight spaces. Or OEM modules for integrate cameras into custom systems. Whether you're not flexible, precision or compactness, we have the right solution. Now let's look on one of our most popular camera series, the VarioCam HD Head. It is a multi-talent, robust, precise and fully industrial grade. It has an up to 67 rated housing and is motorized focus control. The power is possible also over PoE, and this allows an easy integration. The camera is built for continuous operation, whether in test systems, product lines, or also quality assurance. The flagship of the series is the VarioCam HD Head 800 or 900. An impressive resolution allows for extremely precise detection. With using microscope technology, resolution increases to 2048 by 1536 infrared pixels, ideal for detailed imaging. This, in combination with the high thermal resolution, the high accuracy and the right temperature range, make it to top camera in the class. Still with a strong performance, the VarioCam HDX Head. This version is ideal for applications where extreme detail is not required, but reliability and stability are the key. The thermal performance is slightly lower as for the VarioCam HD. This version is also interesting for OEMs or integrators looking for a balance between performance and costs. If the size is important and the flexibility is not so necessary, we could advise the VarioCam HDX Head S. The series is a great option for those needing a compact, robust and a reliable camera. Now to one of my personal highlights, the Taris Mini. This camera is tiny, just 5.5 by 5.5 by 5 centimeters in the standard version, or in the OEM version only 5 by 3 by 3 centimeters, but technically impressive. With a resolution of 640 by 480 infrared pixels, a wide temperature range, and a high temperature resolution up to 20 millikelvin, it is technically impressive. For the compact or mobile applications, the Taris Eye Mini is a top choice. Let's have a more detailed look what makes the Taris Eye Mini so special. Its housing is made of light metal. It delivers 50 frames per second and it's easily controlled via software, such as our Earbus 3 platform or via the SDK. By using open standards, this long-time integration is ensured, making it a true invest in the future. Thanks to its GigE interface, it is easily integrated into existing systems without proprietary solutions. Its control system is vendor independent and simple. Even large image data volumes are transmitted reliably, even at high frame rates. Since the camera is based on open standards, it ensures long-term compatibility. For ultimate performance, our Image IR series is the top choice. These cameras use cooled quantum detectors, extremely sensitive and for fast measurements. They cover both the mid and long-wave spectral ranges, which make them perfect for demanding applications. This series includes more than 10 models, all of which can be configured based on specific requirements, ensuring maximum flexibility for various applications. One of the standout features of the Image R series is its modular design. Each camera consists of 3 main modules. The optical module includes filter wheels, interchangeable lenses or motorized focus. The core module, the main module, it houses the detector, the cooling system and the electronics. And the interface module provides the in and out connections, the GigE or 10 GigE interface. With a wide selections of lenses from 12mm to 200mm, also including microscope lenses, every setup can be easily adapted. One of our most popular models in the Image IR series is the Image IR 6300, a classic mid-wave infrared camera perfectly suited for continuous industrial use. It offers various trigger and processes interfaces, enabling precise, repeatable data acquisition. The power over Ethernet and the web interface also allow an effortless operation. A fascinating topic in the shortwave infrared range is the Image IR 8000 or 9100 series. It offers different sizes of detectors and with different frame rates. If a shortwave infrared camera is needed for your measuring task, this camera is, with extreme short integration time, an ideal solution. Lastly, an often underestimated camera type, zoom infrared cameras. These are not only suitable for auto applications such as border surveillance or early fire detections, but also for laboratory or production use. All zoom cameras are radiometrically calibrated, meaning they provide precise temperature data even over long distances. This allows for both large scales, observations and detailed inspection, without switching the cameras. Here's an exciting solution for special application: the Peerwoods long-wave infrared camera 631. This compact, lightweight camera is available with or without a visible light channel, ideal for inspection tasks requiring both infrared and visible reference images. Its infrared detector provides 640 by 480 infrared pixels and a wide range of different lenses offer great versatility. This system is especially used for outdoor monitoring and inspection applications, where both temperatures and visual informations are essential. The Peerwoods long-wave infrared camera 631 is not only compact, but also highly integrable. It features digital trigger inputs. It is fully compatible with our earbud 3 software. The camera supports modern interfaces such as GigE and even provides a web access. A camera ideal for OEM projects or system monitoring. Of course, we also offer measuring accessories, especially protective housing for our cameras. Whether for indoor or harsh outdoor environments, our protective system resists dust, moisture, temperature fluctuations and vibrations. And, as always, these components are designed for long-term use and easy integration. That brings us to the end of the presentation. Thank you for your attention. I hope you gained a good overview of the infrared thermography and the infrared camera technique. Whether compact or high precision, InfraTec has the right solution for your need.
Okay, so welcome back. Let's move on to the next session about software. Let me share what we have prepared for software.
So now let's have a look into the software part. In terms of software, I've heard an introduction or comparison about lab software and automation software. So first of all, let's start with the lab applications. In the lab applications, it's typically manual operation and analysis, typically in R&D and quality assurance in lab. And the requirements is a higher flexibility to serve a wide range of applications. So the requirement is flexibility, high performance, and precision. Software is mainly used the lab software as our lab software Ibris, and as well as SDK for MATLAB, LabVIEW, or also Python scripts are used. So let's move on to the automation solutions. In automation solutions, it's typically an autonomous operation. There's a process integration and there's a solution specific for one task. And the requirements are a reliable, fast, cost-efficient solution. And in terms of automated monitoring, there is some pass-fail evaluation included. And for 24/7 operation, such called watchdog is needed to supervise the software and to restart the software if needed. In terms of software, there is typically specific software for specific applications, and the integration can be done via GigE Vision or also via camera manufacturer SDK. Let's move on in terms of software solutions that InfraTec is offering. We are targeting two kinds of customers. We have on the right side, we have OEM customers, integrators that integrate the thermal cameras in their solution. So this means there is a third-party software used, and InfraTec is providing the interface for the integration. On the second step, we are offering InnoScan Base as our small automation software. It can target OEMs, integrators, and end users as well. And last but not least, we have the InfraTec turnkey solutions, where we offer a complete solution for end users. Let's now have a look at the first section where we offer a solution for camera integration. The first solution we're offering is the integration via our camera SDK. We offer a so-called IRBgrep SDK for online applications. This SDK allows full management of all InfraTec cameras. It provides full access to the retrometric data in the customer application. There are also add-ons for MATLAB, LabVIEW, and we support Windows and also with limited support Linux as well. In terms of benefits, this SDK operates with all InfraTec cameras, so it's very easy to switch from one camera to another, because we all use the same SDK. And our SDK makes a full feature set available. But in terms of programming, if our SDK is used for programming, there is a requirement to have an experienced programmer on at the customer side. So this is the SDK that we offer. The next option for camera integration is the GigiVision interface. So let's start with some background information about GigiVision GenICam. Before that was available, there was a situation that the vision camera manufacturers were use proprietary interfaces, protocols, SDKs. So there was quite a high effort for software integration, because each camera was different interface, different software. So it was very, very difficult. Therefore, there was some standardization going on, which led to GigiVision and GenICam standard. So there's now a standard interface and protocols that allows plug-and-play software interface. Thermal cameras, on the other side, they are not part of this standardization. So there is also different image data and also other control options that are not included in the standard for vision cameras. So therefore, GigiVision is often used as a basis, but there's always some proprietary features and some adaptation to make it usable for thermal cameras. So to give some more details about GigiVision and GenICam, so first there was the GigiVision interface standard. So this was on the camera side. This is based on gigabit Ethernet interface, and it defines the transport protocol via that interface. Later, there was on the other side GenICam. This was driven from the software side and driven from the European Machine Vision Association. And the goal is to make the camera interface independent, so that the software does not rely on different interfaces. It adds a generic software layer for cameras, so that doesn't matter what kind of interface the camera is using. It's all the same way to talk to the camera. And to do that, there are two things. There is a transport layer, GenTL for transport layer, and a GenAPI for API for application programming interface. And this allows plug-and-play use of cameras and software. And later, this kind of two standards were merged together, so that also GigiVision has adopted parts from GenICam to make it compatible to this standard. So let's move on, a bit more details, because that's very important for use. First of all, the API, the programming interface. This allows access to the camera features and configuration. And how this is done, there is, as we can see here, there is an XML file inside the camera. And this XML file, then describes the features, functions of that camera to the software. So the software can detect what are the features of the camera, and it can allow access to the features of the camera. On the other hand, we have the image acquisition interface. So there's how the camera transmits the data. And there are two possibilities. There is the GigiVision standard that only works for GigiVision cameras, or there's a GenICam transport layer that is interface independent. So there it doesn't matter what kind of interface the camera is using. As we can see here, one example with Halcon. Halcon is a very well-known image processing library, and they are offering two possibilities. It can be the GenICam connector, or it can be the GigiVision connector. And as we can see here, there's two ways to select the image acquisition interface. Now let's move on to a bit more details. As a bit of example with our camera, the Taurus IR Mini. What are the benefits of supporting that interface? So this allows plug and play with software, with standard software. We can use a wide range of applications as Halcon, or also open source software as Aravis. And with this software, our cameras can be used on a wide range of software applications and platforms. Besides Windows, it can be used on Linux, and also, as an example, Linux on ARM is used with the Raspberry Pi. So we have customers also using our camera with the Raspberry Pi, for example. Now I would like to make a live demo to explain that, or to show that a bit more in detail with a sample application with the eBus player or eBus player. You can see it on the right-hand side. I will now show a bit more in detail how we can control with the API and how we can do image acquisition with such software. So let's move on with the demo. Okay, here we can see the eBus player. The first step is now to connect the camera. We select this select connect option. We select Taurus IR Mini, and we press OK to connect the camera. So now the connection process is ongoing. It takes a bit of time to connect the camera. So now we have the camera connected. We can start the image stream by pressing the play button. So now a continuous stream has started. We can see this is a live recording. So this is hot water in a bottle. So we can see below that we are now streaming with 50 Hertz, which is the maximum speed of the camera. So now I would like to show you that GenICam API. So we go into device control. Here we can see this are the parameters or the settings from the XML file that I have explained earlier. And we can scroll down. So there's a lot of features and things that can be set and done. We can, for example, initiate a non-uniformity correction. If I press here, it will make a click and it will make a non-uniformity correction. The function I want to show you now is to reduce the frame rate of the camera. So native, we are now streaming with 50 Hertz. I can reduce that by putting a value into skip frames. So I can reduce the frame rate now to half the maximum frame rate. Now instead of 50 Hertz, we have now 25 Hertz. Yeah, so what we can also see here is obviously there's a watermark on that in that software. That's for evaluation purposes. If it's not licensed, obviously for a real application that wouldn't be there. So there are more things in that software. I can change calibration ranges and so on. I don't want to go into all the details. I just want to show you like the basic concept. So now let's close this. So what we can do now is this software also has some functions to save images or videos. So let's start first with save an image. I can press save current image. And now I go to the folder and I can see that there are also already some existing, and I have a bitmap. I can open the bitmap of that recording. Yeah, so this is an easy way to export single images. I can go now back to the application, and I can do the same also for video. Let's stop this stream. I go to save images or video. I enable the functions to save images or video, and instead of bitmap, I select video. I can make settings of the frequency of the video recording. Let's keep it with the default values. So now it's we see this line below that the recording is initiated, and as soon as I start, we will see that the recording is started, and now it's acquiring a video stream. Let's stop it, and let's go back to the folder. I have now another recording. Let's open the recording. Yeah, we can see very nice and smoothly the recorded video. Okay, so let's now go briefly back to the application. I have explained you all the key functions, how to use the API to control camera settings, how to show images, and how to save images and videos. Okay, so much about this live demonstration. So after the demo, let's now have a look at the InduScan base as a small automation software. So the InduScan base is a cost-efficient system solution for automated thermography. It's for 24/7 use in industry applications. It can be used to monitor processes or can be part of a bigger solution. The package includes up to 3 cameras of ValueCam or Taurus IR Mini. The software, of course, that runs on a small industry PC, and also we support the application and how to set up the system. Let's have a look how the system looks like. We can have up to 3 cameras, 1, 2, 3. It can be powered by Power over Ethernet, PoE. And then we get the inputs from the cameras, and we can use outputs to control other processes. A bit more in detail, as I mentioned, with the up to 3 cameras, there are the contacts I have explained to hand over to other applications as a warning, alarm information. We have data logging possibilities, so to see later what triggers an alarm. It's an easy setup, and it's made for 24/7 operation with the watchdog. Now let's have a look at the system in the live demo. Okay, here we can see InduScan base running. We have the thermal image acquisition we can see on the left side. This is a loop. This is a simulator. This is a loop, so we can see temperature rising and then falling down because it starts again. So we can define 2 values, one for the warning, one temperature for the warning, and one for the alarm. So what we can see, there are already alarm warning messages coming in because we exceed the temperature of 65 degrees. So at the moment, this is for the whole image. What we can do now is to define objects in where we want to measure the temperature. And there are different possibilities. We can make a single point. We can make a line, a straight line. We can make a line with many points. We can make a rectangle. We can make a ellipse. And we can make one with multiple points. So let's now choose this rectangle. We want to evaluate the temperature here on that object. So I make a rectangle right here. And now we can select to show the maximum temperature within that rectangle. Yeah, on the line, it would be along the line. Here it's all the temperature inside that rectangle. So we see how the temperature is rising. We see warning is showing up. We can now, to show you how to set an alarm, we can, if we define the temperature 70 degrees, for example, for the alarm, now we see that an alarm is triggered. Obviously, let's wait again that the alarm condition is long enough. Now we have recording. It's still in the state of recording. So this is how we have defined that. As soon as it's finished, we can have a look at the alarm data. Now it's finished. Now let's look into the data. What we can see here is we can see the data, the collect or the measure or the measured data when the alarm was triggered. So we can verify the alarm, and then we have the possibility to confirm the alarm or to remove the alarm. Let's now remove it. So let's have a look at the settings. At the moment, we have set one camera only. We can define up to 3 cameras. I will show briefly how that looks like. We can define the frame rate for the acquisition. We can define a delay. So the alarm condition or the warning condition has to be present for some time. So we can eliminate like false alarms. It's also possible to export the data as video. So there's many options to choose, or we can also save snapshots. So now let me show you how it looks like with the 3 cameras. So I select now all 3 cameras. I save the settings. Now software wants to restart. Now software is starting again with 3 cameras. It takes a bit of time. So we can see the same logic as I have shown before with 1 camera, now with 3 cameras. Okay, yeah, so much about InduScan base. Okay, so after the demo, let's move on to the last section of the software solutions. We have InfraTec turnkey solutions, where we offer a complete system solution for green energies, electronics, and metallurgy as an example. And more of that you will see in the next session. So thanks, and let's move on.
Okay, so welcome back. So let's now move on to the next session, where my colleague will introduce the automation turnkey solutions from InfraTec.
Yes, hello, ladies and gentlemen. My part now is to talk about our turnkey solutions, and I would give you some overview about these applications. So you see here on this first slide the fields of applications we have. So it's starting from electronics or PV applications up to hot forming, press hardening process, to early fire detection systems, a lot of automation solutions in the automotive industry, in the steel industry, for example, for slack detection or for little hotspot detection, or in substations for grid detection, or for very high-speed applications like for disk or brake disk monitoring. So I would start with our electronic lock-in thermographic system you see here on this slide. And it's a system which you can use for failure analysis in electronics. You see on the slide here that there are several components which helps for this failure application. The main component is the infrared camera. It can be used with different lenses, microscopic lenses for sure. Also, we integrate in the system different power supplies for giving some electrical signal to the sample you want to detect. And it helps you to see power loss in this application or short circuits in this application. Yeah, so you see on the chamber, it's big enough that you can have different sample sizes in this. And there is a powerful customized software you can use to see very fastly the effects of failures and to detect even failures, which are far below the detection range of the camera itself. Because the signal we are using for this is a lock-in signal, so an electrical wave, which will be placed to the sample. And with Fourier transformation, we finally can see these hotspots in this. So additionally, there are components like visible microscopes, an XY table, which helps you, for example, to make a stitching mode in this application. And we can also use the system and integrate, for example, wafer probing systems. So the principle of this is that we have a perfect synchronization between the thermographic camera, the image IR, and the power supply with the PC. So the signal is coming from the camera to the PC, and there will be an excitation trigger signal to the power supply, which will be in this cases for PV, solar cells or solar modules or ICs and chips by electrical signal. And finally, if you give this signal to the component, and if there is a failure inside the sample, it will be giving a different heat transfer, which comes then to the surface, and it's possible for the camera to detect. And very slightly temperature differences inside the object will lead then finally to this object detection, so for failure detection in this case. So this makes it possible to see even below 1 millikelvin failures in the sample. And if you measure for longer times, you can even measure microkelvins in this feature. Additionally, the camera with the resolution of HD with 2560 pixels by 2048 pixels makes it possible, for example, for a chip like this to have a very high resolution. And here on this slide, you see, for example, the field of view from different optics and lenses. Here, for example, a chip which is about 10 by 10 millimeters. With a standard lens and a close-up additionally, which reaches then a pixel resolution of 60 micrometer per pixel. Here with one-time magnification lens, you get already 10 micrometer per pixel. And here with 2.5 microscopic lens, you're reaching 4 micrometer per pixel. And finally, the highest resolution you can reach is then with the 8-time or 10-time magnification lens up to 1 micrometer per pixel. Good, here a sample with an iPhone. For example, in this case, it's the touch sensor we are inspecting now. And this is the overview with a one-time magnification lens with 10 micrometer per pixel. Here, 4 micrometer per pixel and 1.3 micrometer per pixel with the 8-time magnification lens. And the good thing is that this touch sensor here is for infrared transparent, so you can directly measure here, in this case, if there is any defect on the chip, for example. Good. The same works for all types of different solar cells, for amorphous silicon types, for multicrystalline types, for monocrystalline types, for PERC cells, for CIGS modules, for example, and not just for cells, it also can be used for complete modules. So I told you that there is a possibility from the automation team to integrate different stages, like an XY table, for example. And this makes it possible to have, for example, with a microscopic lens, a very high resolution if you move over the sample and make different single measurements to have finally a stitching mode, which can then combine and have this resolution 1.25 micrometer for each pixel. And finally, for example, this small sample area of 10 by 10 millimeters will be then stitched together in a 4x4 matrix. And yeah, this can be easily reached then a high resolution completely for the complete sample. So if, for example, the board is 80 by 80 millimeter, you can finally reach then 1.3 micrometer per pixel with the 8-time magnification lens. Another possibility, this is so-called macro batch mode. So you can program in our software, in this automated software, for example, different lock-in frequencies. So starting, for example, with 1 Hertz, then going to 5, 10, 20 Hertz. And then each measurement is made after each other. And finally, all the sample measurements are laid then together. And finally, so it's possible to go in a depth analysis of the sample. So to see even in which depths the failure is happening. So not just to see that there is a hotspot on any location on a chip like this. So even to see if it's more related to the surface or more in the sample, more deeper inside the sample. So this is the typical software layout, our active online, Urbis active online view. And you see on one view here is the live infrared image. You have here the amplitude image, the complex image and the phase image. And with this information, you see on one view where are hotspots, for example, in this IC, and with the phase information and complex information in which depths the failure is happening. If, for example, there is a multi-layer design in this area, it will help you to analyze the depths. So on the left side, you see the parameter setup for the lock-in thermography. So in principle, it's the lock-in frequency, the measurement time, and here you have some features, for example, like the batch mode. You have the possibility not just to see that there are failures, inhomogeneities on a chip like this. You can make also emissivity corrections for each pixel inside the sample, and so make also real temperature mapping on this. So use it for failure analysis in chips, but also for real temperature measurements on components. And from the sample size, you can use big PCB boards like 30 by 30 millimeters up to very tiny chips, which are just 2 by 2 millimeters or even smaller. Yeah, another sample here, you see a live measurement. And this is now created here to see, for example, several merging options you have in the component available. Okay. Another possibility to make the resolution a little bit higher is a so-called solid immersion lens, SEL. So this is used and can be used in combination with, for example, the 3-time or 8-time magnification lens. So this is made also of germanium, this lens, and it helps to make 4 times better resolution finally. This solid immersion lens will be placed directly here on the substrate, on the sample. And finally, it makes it 4 times better, the smallest pixel. So you see on the left side here, without the solid immersion lens, the resolution, and here with the solid immersion lens. So next application I would like to give you some overview is our press check. So this is the monitoring solution for hot forming. It's a complete automated solution. And in this process, we have several requirements from the process of temperature measurements. And this is made, so sheets, metal sheets are heated up in a furnace up to 900 degrees Celsius, are pressed then inside the press for about 10 to 15 seconds. This time you're reaching then the forming of the part and also the hardening of this part. So it's important to measure the temperature after the furnace, before pressing, after pressing, and sometimes also after the pressing on a conveyor belt. For this, we have a flexible camera positioning, and this helps for each press layout to adapt our system. And here with this physical background, I would give you some values because it's important to measure for the different temperatures you have in this process and to use also for this different cameras for each temperature range. So for the high temperature, like 950 degrees before pressing after the furnace, it will be in this range. And you see with a 1 micrometer range, you have the highest maximum of radiation you can detect with this camera. And for this reason, we measure for the high temperature with a 1 micrometer wavelength camera. Besides this, after pressing, you want to detect the sheets with about 200 to 300 degrees Celsius. And there will be made an additionally measurement after pressing also on the tool side, which can check, for example, if there's tool wear on this. So the measurement range for this camera is between 30 and 300 degrees Celsius. And so we're using for this our long wave VarioCam camera with a very high resolution. So here are some samples about the different locations. You can use it in a press. So here in the background, you see a press like this, and this is our evaluation unit, which integrates industrial PC, the specialized software, which makes it for the operator very easy to detect if there is a failure in this kind, for example, a problem with the hardness level of the components, or for example, if there's a position failure inside the press, or if the press tools, for example, are not cooled correctly. This can be also seen with the monitoring and with our cameras. So here, the camera for the hot side. This is also an HD resolution camera we are using for this. And the second advantage for this high resolution is not just that you can detect much faster any hotspot in these sheets. You can also detect if the position is okay or not okay with this high resolution. And this makes it even possible to detect, for example, the angle here of these parts, if there's any other incorrect positioning, if there is a double sheet inside the press, or finally, if there are other problems coming from the furnace, for example. So here a special application we have, for example, for one customer made. This is a special adapted housing for this customer because the feeder was hiding too much area of the sheets from top, so we could not measure from top side. And for this reason, we implemented here a special housing, which allows to make the measurement from the bottom side of the sheet. And so this needs, because of this dusty environment, to make a special protection with an air knife and a special lid here for protecting the lens, which is underneath here. Another sample here, why high resolution makes a big difference is here. You see on the left side, the high resolution with the VarioCam HD in XGA resolution, 1024 pixels by 768 pixels. In difference to this, on the right side, a typical VGA resolution, 640 by 480 pixels. We have both cameras available, but you see very easily on the left side, it's much easier and faster possible to detect any hotspot here, which is not showing, at least on the right side, or in a much longer way, or even not possible to detect. So there's a clear advantage to use this high resolution for this process. The next application coming is now for very high speed and rotating objects like tires or brake disc. And you see here the fast turning brake disc. And we have here, in this case, a special camera and a very high speed camera, which uses a line scan just of the detector. So the principle is on this slide here, you see there is a dynamometer which rotates the brake disc, which is here mounted. The camera, it's directly here in front position of this brake disc. And if you have here the top view, you see the camera looks here on this brake disc. And we have additionally two mirrors, one mirror from the left side and one mirror from the right side. And so it's possible to detect with one camera and using a line scan, going from left side to the right side, directly to detect both sides of the brake disc in one view, and this at a very high speed. So it can be measured up to 300, 400 kilometers per hour. It can be used for motor brakes, car brakes, and train brakes. So for different diameters. And yeah, it's possible to see any inhomogeneity on the parts. And this is the video for a real measurement of a brake disc. So you see the line scan here on the left side, for the left side of the brake disc, here for the right side of the brake disc. And the software automatically combines both views from both sides so that you have the possibility to see on one view left and right side of the brake disc. And finally, what you want to have is a homogeneous temperature on the brake disc for braking, and not just hotspots. Like you see any critical point here. You even see the cooling holes of the brake disc. So this little small holes here in the brake disc are the cooling channel of the brake disc. So another application is our so-called grid detection system. So this will be used for 24/7 operation in substations. So we monitor with this system critical points in a substation. And this is possible also by a very high resolution of the infrared camera. And also we normally have there integrated, for example, pen-tilt head operation to work really with this high resolution in a 360-degree range in a substation, and also having here a second camera, a visible camera, to use merging modes in this application. So also there are available zoom lenses. You see, for example, an option here with a zoom lens, which gives you even a higher resolution with this camera additionally. Also, special design of the housing, which is made by InfraTec, with wipers, for example, with some flushing systems, and also very special pen-tilt head operations, for any environment, outside or inside. Typical installation here we have on the highest point on a substation like this with the system. And again, the very customized software for this, which allows manual operation, but normally these solutions are made fully automatic, so that even in case there is a warning or alarm inside a substation, there will be given an automatic alarm to a system, to another plant management system, or even by automatic SMS or other mobile devices. It can be done by mail, for example. InduScan application, my next point is just standard industrial scanning applications. And here you see a typical layout for a system. So in each case, we have a thermography camera, which is directly connected then to a main control unit, which has an industrial PC integrated, and several interfaces, which communicates, for example, with signals from the PLC from the machine. You have here the view inside this electric cabinet, and mostly we have here a display and keyboard unit and a signal unit, which gives you any warning or alarm in case if there is some problem. Yeah, all components are automatically tracked. If the cameras have power, if there is alarm for some unit inside the system, there will be an automatic temperature time profile. Here we have a multi-language integration. So for each language you have, it can be easily adapted in your language. All cameras on one view, automatic logging for the functions, histories functions, and also recipe management for different sample setups, for example, can be loaded and stored inside the system. Yeah, also here a special application we have for die casting or forging processes where cameras are used to monitor special machines, for example, die casting machines or standard, for example, paper machines where a hot ball bushing or something can heat up, and there will be, if this is happening, there will be given automatic alarm to the master system. Another application I want to jump now is the laser plastic welding, where we have also available cameras. So the laser plastic welding is a process where with a laser, mostly electronic components, but also medical devices are welded together. And in this case, we use directly, it's a passive thermography, we use the temperature from the process to evaluate if there is a good contact or a good welding finally in this. And this can be seen here on the screen, green sample areas here to see on one view if there is a correct connection with this. And we would see directly if there's any disconnection in the process. So this is how it looks infrared from the live infrared image, and working with some algorithms we have here on top of this, because we have several pictures for the process from 30 Hertz up to, with our high-speed cameras in the range of 300 frames per second, we can analyze the process and make then adapted evaluation of a good welding or not a good welding. So some devices you see here in the sample from car keys, medicals, and a lot of automotive sensors are welded like this. Another process we could also analyze is for the welding process of metals. For example, here we have a laser welding on a metal part. And in this case, you cannot directly use the temperature from the welding process. But in this case, we make an after treatment of this welding with some induction heating. And because of this, you can finally see if there is the welding correct again or not correct. And you see here some sample image of the welded parts. And here another application where a car body is inspected by two robots in this case. This is used for spot welding of metal. And the thing here is that both of the robots have an infrared camera and image IR in this case, and also the excitation source to give energy on the welding spot and then directly look, because of the heat transfer, if there is a good welding or not a good welding. So if there is a nice heat transfer, this means there is a good welding. If it's not really good connected, there's a bad heat transfer. And this can be analyzed then later with sophisticated software from us. Good. An application also I would like to highlight is our solar power tower control, so-called SPTC. And this is used for solar towers, which are common. We have also one solar tower in Germany, which is for R&D level, but also we made projects, for example, in the Atacama Desert in Chile or in China in the desert. And the principle is you have a big tower in the area of 200 meters high. And here you have absorbers, which can heat up in the area of about 800 degrees. And this is done by surrounding reflector mirrors, which collects the sun and reflect this power to this receiver. And with this 800 degrees, you're heating up a kind of liquid from salt and oil. And this makes it possible then to use it also with a turbine and then a generator. You can produce electricity. And the good thing is that you cannot just produce energy during the day when the sun is shining. This oil mixture, salt mixture, you can also transfer in the evening in this special reservoir. And then you can also produce energy during the night with the turbine. So all around the clock, you can produce energy with this application. And the thing is, you have to check that the absorber is not overheating and not getting too cold, so that you have a very homogeneous temperature profile here on top of this. And here you see the temperature profile. So this is the tower in Jülich, Germany we have. So we have just 1/4 here as a mirror field. And how it looks in the desert, you see here, there is a much bigger mirror field. You have a much higher tower, so like up to 200 meters high. And the distance from the camera, which is located, for example, here in this area. So the distance from the camera to the absorber is about 330 meters. And this means because we have to detect here the absorber all around the tower. So this means in this case, we have here 8 cameras located all around the tower, and they are controlling the single tubes of this absorber. And one tube has a diameter of about 50 millimeter. So this means we have at least one measurement point on this distance, and this can be reached by this high resolution of 1024 pixels by 768. And we also developed for this application a special Taylor lens with 265 millimeter. So you see it here, special housing, which directly looks here on this absorber areas to monitor each of these panels, and all single tubes can be evaluated. And finally, with this information to the master control PC system, all the mirrors around can be positioned and can be coming into effect or not into effect. So they are positioned by motors to make here a mostly homogeneous temperature area on the absorber panels. So one more application we have here by InfraTec is our early fire detection system. And it's really early fire detection, so that something like this, like a fire, is never happening. And this means we detect a hotspot already before a fire is starting. So we implementing these systems or have implemented these systems very often here in Germany for waste to energy plants. So you have here the view inside the energy plant, which is very dirty environmental here. And we detect or want to detect very early here, for example, created hotspots, for example, of a chemical effect, or for example, a battery, which is heating up here on a component and which could lead to a fire finally. And we catching this before a fire is happening. And so this is the very, very early stage when the temperature is rising. So already in the area of 50, 60 degrees Celsius, we give a first warning, and then with 80 degrees, we give already an alarm if it's more heating up. So we don't have to wait until smoke is happening or even a fire is happening, where other sensors are much later in the time of detection. Yeah. So this is the thing that we have an early fire detection system. Yeah, we have different cameras available for this, different resolutions for the cameras. We have different housings. We have the combination of just infrared or infrared plus visible cameras for having a merging mode for a better orientation inside these plants. We have the combination of pan tilt head options, so to use this high resolution of the optics in the complete area, and also to have a bigger monitoring area for the complete object. And here on the right side, you have the again the sample for the control and the evaluation unit. Yeah, you see, just as a sample here on this picture, how dirty such environments are, but still there is a lot of dust covering the camera, which is behind here, but still the optics is free because of a special air flushing we are using that you do not have any maintenance to do on the system. The flushing of the lens is completely maintenance free, so that there's every time fire detection or hotspot detection possible for this process. Yeah, on the left side, again, waste to energy plant, or on the right side, other plants, indoor plants, where you have, for example, shelves and racking designs where you can use cameras like this, or later I will show you another component we have available for this special situation for very narrow areas in a storage like this. Yeah, again, the customized software for processes like this. So typically we divide the plant or the monitoring area in different sectors, and all sector is then monitored with the pan tilt head operation. So you can, in this case, manual check, for example, if there is a hotspot detected, or the standard mode is an automatic mode. So if any hotspot is bigger, for example, than 50 degrees or 60 degrees, there will be giving a warning for this. If it's even more heated up, there will be an automatic alarm to the system. And we combine our systems in most cases also with automatic fire extinguishing system, so that in a very early stage, this hotspot can be extinguished, cooled down, or deleted finally, in this case, so that no fire breaks out. And yeah. Another application for early fire detection is here on this image. So for example, cameras on a conveyor belt, which detects, for example, shredded material, for example, components like wooden chips, for example, and could create some hotspot because of the shredder. If there are metal parts inside the wood, this could lead, for example, to a hotspot or even fire, and this will be automatically monitored here on this conveyor belt with our cameras. And from the cameras, we can integrate in our system from single camera systems up to multi-camera systems to 10 or even 100 camera systems. We can combine them together and then all combined in this evaluation unit, and depending just by different PCs, then connect all this data and to transfer this to other machines. And here was the slide I want to show you, that for each design, for each storage, we have different layouts also, from the camera resolution up to the layout. For example, here are single assembly manufacturing positions, up to this storage design we have, where we have smaller cameras with smaller resolution looking on the opposite side here in these shelves, or going here on this area where you have pallet storaging here on the floor level, and use just one camera here for this big area. So easily you can catch with one camera here 50-meter area in this direction, and also 50 meters in the other direction. So Depending on the site and the storage, we can adapt this from different resolution cameras up to different pen-tilt head operation, combination of visible cameras and infrared and so on. Yeah, this is the camera, for example, for the smaller, with the smaller resolution, we're working. If the area in a shelf is very narrow, we use just 80 by 64 pixels, or newer applications, 160 by 120 pixels. Another sample here, if the area needs an ATEX certification, for example, in chemical plants, LNG terminals, for example, we have a special housing available, and also with pen-tilt head operation. Yeah, and last slide or applications I want to highlight here is in the steel industry, going, for example, for steel bars monitoring, flushing systems on the steel bars, for torpedo car monitoring. So typically the isolation material is checked there with our cameras. For slag detection, you see here, we are using there the big emission difference between slag and steel for working, that no further slag is used for the other process later, so that we give a clear signal if there is slag detected and the process is stopped. Then for ladle hotspot detection, this is the same application like for torpedo cars. So we check the outside shell of this ladle, and here another sample for this slag detection housing. So the benefits for you working together with InfraTec, that we have a long experience in the different applications, not just this applications, also for a lot of others. We have already 600 automated solutions in the market, in the worldwide market, and that we are responsible together for one, for the hardware, for the software, and finally also the complete project management and development, and up to the service and maintenance you have finally for your object. So thank you very much for your attention, and I would like that if there's any question, please give us a mail or call. We will help to give you some information for your application. Thank you.
So we are now ready for the question and answers session. We already have some questions, so please, if you have some more questions, please type them in so that we can answer your questions.
Yeah, Thilo.
Please go ahead and start.
Yeah, thank you very much, Thilo. We already got some questions, and I mean, it's not so much time left, so I will directly start with the questions we already received. So if there are any more questions, please fill in, and we would like to answer them. So the first question is, at what frame rate does it make sense to use a photon detector instead of a microbolometer? At what frame rate? It depends on the measuring task. So a microbolometer is not so dynamic as a photon detector because of the time delay. To make a picture needs more time, and if you have a very dynamic process, the temperature changes can't be measured so fast as with a photon detector. So we always advise up to a speed of around 50-60 Hertz. That is possible to measure this exactly with a microbolometer, and otherwise we would advise to use a photon detector. Then another question, and I think I will, would be nice, Thilo, if you could answer this question. Do all InfraTec cameras support Gig Evision or GeniCam?
Yes, not all cameras, but most of the cameras. So we have spoken about the TARES, about the VioCam, so the compact cameras. For the image IR, we have a new generation of image IR that will fully support GigaVision and GenICam. So we have some limited support already now, but the full feature set will be available with the new generation of image IR.
Okay, good. Thank you. The next question is here. What materials are used for infrared windows and protective housings? What materials are used for infrared windows? That's depending on, first of all, the measuring task. And let's say also for the camera that you would like to use, depending on the wavelengths that the camera is used. For mid-wave systems, for example, Sapphire is often used because of the hardness and the possibility really to produce it, and because of also it doesn't have so much influences of temperature changing. If you have a camera or you use a long wave camera, there are different materials used like gallium fluoride or germanium, for example. But these materials, depending on the measuring task, they have some influences depending on their own temperature, for example, that they lose some transmission or other things. So it really depends on the measuring task and the environment you will have. Then you will choose which type of material is the best for the solution. And here another question. Thilo, that's also for you. That also goes in the direction of GigaVision and GenICam. Which third-party software can be used?
Yeah, so thanks for the question. It's all kind of software that supports GigaVision and GenICam. Of course, then it depends on the camera, on the feature set, what features are available. But in general, if the software supports GigaVision, we can get the image data across, and if it supports GenICam, we can control the camera. And for details, please get in contact with us, and we will then, based on the combination, we can help you with the available feature set.
Yeah. And then I have here another question. Is it possible to set a mirror along the optical path? Can it be standard mirror or must it be special and refer to the automatic brake analysis? Okay. Is it possible to insert a mirror along the optical path? Can it be a standard mirror or must it be special? I refer to the automotive brake disc analysis application. It needs to be a special mirror because glass is not so, the properties of glass for the reflection of the infrared radiation is not so good as, for example, of metal surfaces, for example, or other materials. So it's special type of material. Glass in this wavelength has the properties to absorb a lot of the radiation, and that would not so much help you for the measuring task. Okay, then the next here, any station for fire protection, some call to spoke about possibility radiation. Mr. Zirik, we will call you to talk about the fire protection. That is no problem. And then here, okay. Yeah, let me have a look again. Mirror, can you tell me how? Yeah, okay. So, that were all now.
I found one more. How do you keep the objectives clean in industrial environments? So I think one was mentioned is like air flushing. This is yeah, of course, you can use a protection window in front to protect the lens, but then still you have to make sure that this doesn't get dusty. So it's yeah, air flushing. Some applications also, as you have maybe seen in the presentation, you can make a lid, close the lids, then that you protect the camera when it's not used. So there are multiple ways to deal with dust.
Mm. Okay, so
I think there were several questions about the presentation. Yes, it's possible to get the presentation. So we will ask you to give us a feedback for the webinar, and we will also then send out the presentations from the webinar.
yeah, that's correct. That's correct. Good. Let me have a look. That were all of the questions. When I see it correctly. Yeah, then I would like to say from my side, thank you very much for your time. I hope you enjoyed the presentation and that you will receive the information you need. If there are any questions left, if you would like to talk with us, we would be happy if you can call us, and you can reach us per mail or also by phone. And yeah, again, thank you very much for your time, and I would like to give the last words to Thilo.
Yes, so thanks very much from my side as well. So we have some more questions, but quite kind of specific ones that we will follow up directly. Yeah, I think it's maybe then too specific, some things for the big group. So please give us time to look into the question and maybe also ask some more details, to really understand that. So it's not forgotten. So there's some more kind of specific questions, and we will follow up directly. So thanks for your time, and I wish you a nice day.
Yeah, have a nice day. Bye.
Bye bye.